What are the eigenvalues and eigenvectors of 1, 1, 1, 1? Well, let's check that out. As usual, the matrix A times its eigenvalue x is equal to the eigenvector of the matrix lambda times its eigenvalue x. Subtract lambda x from both sides, we have ax minus lambda x equals 0. Factorize, you have x outside the bracket, a minus lambda equals 0. But since a is a vector and lambda is a single number, you cannot subtract them like that. It must be vector. A is a matrix and lambda is a single number. You cannot subtract them just like that. You need matrix minus matrix. So to turn this into a matrix, you multiply lambda by I. And then a minus lambda I. The determinant of that is 0. So, here now, A is the matrix 1, 1, 1, 1 minus lambda times identity matrix 1, 0, 0, 1 is equal to 0. Now, let's see what happened. 1, 1, 1, 1 minus, when you multiply out lambda, you get lambda 0, 0, lambda is equal to 0. By the way, so the determinant that we want, the determinant of that is equal to 0. When you subtract these, we get 1 minus lambda, 1 minus 0 is 1, 1 minus 0 is 1, 1 minus lambda is 1 minus lambda. Alright. Oh, by the way, it's determinant that I want. So let me put the vertical lines equals 0. Alright? Now, here, we find the determinant. It's 1 minus lambda times 1 minus lambda minus 1 times 1 is 1 is equal to 0. So we multiply out 1 times 1 is 1, 1 times negative lambda, then negative lambda times 1. You're going to get negative lambda minus lambda, which is given minus 2 lambda. Negative lambda times negative lambda is plus lambda squared. Minus 1 is equal to 0. Alright? When we put these together, we get lambda squared minus 2 lambda. 1 minus 1 is 0. So the ones are gone. So what we get is 0. You see that? Now factorize. Lambda times lambda minus 2 is equal to 0. Lambda times lambda minus 2 is equal to 0. It is either that lambda is equal to 0 or lambda minus 2 is 0, which means lambda is equal to 2. So we have two values here. Now, these are the eigenvalues. We want the eigenvectors now. Remember, when we have A minus lambda I, x equals 0, A is the matrix minus lambda I. We had worked it out and we got this for A minus lambda I. Alright? Times x is 0. So we rewrite this as 1 minus lambda, 1, 1, 1 minus lambda. You see, this is the matrix 1 minus lambda I times our vector x, y, the eigenvector, is equal to 0. Now, we have two values for lambda. Lambda equals 0 is one of them. When lambda is equal to 0, and by the way, since we have two different values, let's call this lambda 1 and lambda 2 to show them as different. When lambda is equal to 0, what happens? You have 1 minus lambda, which is 1 minus 0, which is 1, 1, 1 minus 0, which is 1, times x, y is equal to 0, 0. Let's turn this into a matrix, alright? So 1 times x is x, plus 1 times y is equal to 0. 1 times x is x, plus 1 times y is equal to 0, alright? Now, here, you can see from this that x is equal to negative y from both of them. So, if you have your x, y, since x is negative y, so you must take y and multiply by a negative 1. Because saying x is negative y means the same as x is negative 1 times y. So let y be 1. And you multiply it by negative 1 to get x. 1. And then x is negative 1. So it's negative 1, 1. Or, if you want to, you could make x1 and the y negative 1. It works out the same, alright? Because 1 plus negative 1 is equal to 0. And negative 1 plus 1 is equal to 0. Whether x is the negative 1 or y is the negative 1 doesn't make a difference. See that? Now that's what happened when you have lambda equals 0. What happens when lambda is 2? Let's see. When lambda is equal to 2, what's going to happen? 1 minus lambda becomes 1 minus 2. So 1 minus 2. Then you have 1 minus 2. 1 minus 2 times x, y is equal to 0, 0. So this will work out as 1 minus 2 is equal to negative 1. And this 1 minus 2 also becomes negative 1. Let's multiply. Negative 1 times x is going to be negative x plus y equals 0. And if you work this one out, 1x minus y is equal to 0. If you multiply throughout by a negative 1, in this equation here, you get negative x plus y equals 0. So it's the same thing. Now, it means x is equal to y. So our eigenvector here can be written as 1, 1. So here, our first eigenvector, when x was 0, the eigenvector, when lambda eigenvalue was 0, the eigenvector was 1, negative 1. When our eigenvector is 2, then when our eigenvalue is 2, the eigenvector is 1, 1. Let's see something here. Our original matrix A is 1, 1, 1, 1. 1, 1, 1, 1. This times x, our x, our in this case our eigenvector is 1, negative 1, okay, times 1, negative 1 is equal to lambda times x, 1, negative 1. What was lambda? It was 0, right? Our first lambda here was 0, so it's 0. Now 1 times 1 is 1, plus 1 times negative 1 is negative 1. 1 times 1 is 1 plus 1 times negative 1 is negative 1 equal 0 times 1 is 0, 0 times negative 1 0. So here 1 minus 1 is 0, 1 plus negative 1 is 0. Okay, so that shows us what happened. Now what about when lambda is 2 and our vector, eigenvector is 1, 1? Let us see. Our eigenvector is 1, 1 and our lambda is 2. So A, our matrix, is 1, 1, 1, 1. Times x, our eigenvector was 1, 1. Okay, let me erase this one, get it out of the way. Is equal to lambda. Lambda was 2 times x, which is 1, 1, our eigenvector. So we're saying the matrix times eigenvector is equal to the eigenvalue of the matrix times eigenvector. Let's work this out and see what happens. 1 times 1 is 1 plus 1 times 1 is 1. Good. 1 times 1 is 1 plus 1 times 1 is 1 is equal to 2 times 1 is 2. 2 times 1 is 2. You see that 1 plus 1 is 2. 1 plus 1 is 2. So they work out to be the same thing. A times x equal lambda times x. So instead of having the whole matrix multiplied by its eigenvector, we could just say use the eigenvalue of the matrix times its eigenvector.